Hello students, in this video we'll discuss about the three-phase induction motors. We'll quickly revise the formulas of three-phase induction motor, then we will go to the practicing some questions in the three-phase induction motor. So first we'll see what is the basics of three-phase induction motor. So three-phase induction motor converts three-phase electrical energy into mechanical energy. Mechanical energy is nothing but what? Rotation. So in three-phase induction motor, again we have stator and we have rotor, and stator carries stator winding and rotor carries rotor winding. So quickly we'll see what is the operation of the three-phase induction motor. So we give three-phase AC supply to the stator winding, then rotating magnetic field is going to be developed. Rotating magnetic field which rotates at a synchronous speed, that is 120 F by P. And stator and rotor are not physically touch with each other, they are separated by small amount of air gap. Whenever three-phase AC supply is given to the stator winding, this rotating magnetic field is developed, and rotating magnetic field will pass through the air gap and touches the rotor conductors. On the rotor we place the rotor winding, rotor conductors, and initially rotor is in the stationary condition. Rotor speed n is equal to 0, and rotating flux touches the rotor conductors. So rotating flux speed is nothing but what? Ns. So this flux speed is ns, but conductor speed is what? 0. Therefore here you see flux speed is ns and conductor speed is 0. There exists a relative speed difference between flux and conductor, then EMF will be induced. According to Faraday first law, whenever conductor touches the conductor, then EMF will be induced. So in rotor conductors we will get some EMF. As rotor windings are closed, then we will be getting some current in the rotor winding. So because of the current in the rotor winding, some flux will be developed in the rotor winding. Now we have two flux, one is stator flux and other one is rotor flux. Because of the interaction between these two, stator and rotor flux, then torque will be developed on the rotor conductors. When the torque exerts on the rotor conductor, then rotor started rotating at n speed. So we have given three-phase AC electrical energy to the stator winding, then torque exerted on the rotor and rotor started rotating. Now you see flux speed is ns. Now rotor is not stationary, rotor started rotating at n speed. Still this rotor speed n value is less than the ns value because of the inertia of the rotor. As the speed difference is still there, then we will be getting the EMF. Let us say if the rotor also rotating at flux speed, then there won't be any EMF, there won't be any current in the rotor winding, there won't be any flux in the rotor winding, and the rotor flux becomes 0, only stator flux will be there, and there won't be torque on the rotor windings. Quickly I'll revise again. Three-phase AC supply is given to the stator winding. Three-phase AC supply is given to the stator winding, and the rotating magnetic field is going to be developed in the stator winding. This rotating magnetic field passes through the air gap and touches the rotor conductors. And when this rotating magnetic field touches the rotor conductors, the EMF will be induced in the rotor winding. And this, as the rotor windings are closed, so EMF is there, closed circuit is there, some current flowing through the rotor winding. This rotor winding current will cause some flux in the rotor winding. So here rotating magnetic flux and rotor flux, because of these two fluxes, torque will be exerted on the rotor conductors, then rotor started rotating at n speed. Initially rotor speed is equals to what? 0. And here we call speed difference between flux and rotor conductor with respect to flux speed. So this we call as slip of the induction motor, three-phase induction motor. Ns minus n divided by ns. Very very important formula. Slip is equal to ns minus n divided by ns. Ns is the flux speed or synchronous speed. N is the rotor speed or three-phase induction motor speed. And what is the formula of ns? Ns is equal to 120 f by p. Now at standstill condition, so initially rotor at standstill condition means rotor speed n is equal to what? 0. You substitute here. This is called standstill condition. At standstill condition, what is the slip value? Let us see. Slip s is equal to ns minus 0 divided by ns. Then slip is equal to what? 1. So at standstill condition, slip value is what? 1. And from this formula, if I calculate the n value, I will get n is equal to ns into 1 minus s. This is also very very important formula. So based on the rotor type used, we have two types of induction motor. We have two types of induction motors, that is squirrel cage induction motor, and other one is slip ring induction motor. So in case of slip ring induction motor, we can add some additional resistance to the rotor with help of slip rings. So this additional resistance is a variable resistance. By varying this additional resistance, we can improve the starting torque of the induction motor. We can improve the starting torque of the induction motor. We can also improve the power factor of the induction motor. But whereas in case of squirrel cage induction motor, it is not possible to add the additional resistance. It is not possible to add the resistance into the rotor circuit. So rotor winding resistance is fixed. Now quickly we will see the formulas of the three-phase induction motor. So we told whenever three-phase AC supply is given to the three-phase induction motor, rotating magnetic field is developed. This rotating magnetic field speed is 120 f by p. P is the number of poles in the stator winding, f is the input power supply. And slip formula is ns minus n divided by ns. Very important form. N is the rotor speed or induction motor speed, and ns is the synchronous speed. And what is the formula? N is equal to ns into 1 minus s. What do you mean by slip speed? The difference in the flux speed and rotor speed is known as what? Slip speed. Very very important. Slip speed. At standstill condition, what is the rotor speed? Rotor speed is equal to n is equal to 0. Then we get the slip s is equal to 1, or we call as slip is equal to 100%. When the rotor is rotating at synchronous speed, that means n value is also equal to ns. Then ns minus n becomes what? 0. So slip becomes 0. Usually the slip value is in between 0 to 1. Now about the rotor winding current frequency. Rotor winding current frequency f dash is equal to sf. This dash indicates it is a rotor. R is a rotor. So very important formula, f dash equal to sf. If the rotor is not rotating, slip becomes 1. Then f dash is equal to f. We will get the f dash equal to f. Rotor winding frequency equal to input supply frequency when the rotor is at the standstill condition. And you see these two represent the rotor. R represent the running condition. So rotor winding resistance x2r is equal to sx2, and e2r is equal to se2. And x2r is a rotor reactance per phase, and x2 is a rotor reactance per phase under standstill condition. R is not represented means it is at the standstill condition. And rotor impedance equal to resistance plus reactance R2 plus jx2. Rotor impedance under running condition R2 plus j sx2, because x2r is equal to sx2. And current is equal to voltage by impedance. I2 is equal to E2 divided by root of R2 square plus x2 square. And under running condition, SE2 divided by root of R2 square plus SX2 whole square. These are some important formulas. But in all these formulas, very very important formula is rotor winding, rotor current frequency rho is equal to f dash equal to sf. Next rotor power factor is equal to R by Z. So rotor means R2 divided by Z2, and this is a formula. Under running condition, this is a formula R2 divided by root of R2 square plus SX2 whole square. And again, very important thing is torque developed by the induction motor formula KSU2 square R2 divided by R2 square plus SX2 whole square. So starting torque of three-phase induction motor, substitute S is equal to 1 here, then we will get the formula KE2 square by R2 square plus SX2 square. You see, starting torque is proportional to input supply voltage square. Very important, starting torque is proportional to input supply voltage square. If I change the input 10%, starting torque is going to be changed by 20%. Condition for maximum torque in the three-phase induction motor is R2 is equal to SX2. Very important formula. R2 is equal to SX2. From this, if I calculate the slip, it becomes R2 divided by X2. That means at particular this slip value, the maximum torque is going to occur. Therefore, it is called slip corresponding to maximum torque. Condition for maximum torque in the three-phase induction motor under standstill condition, again S equal to 1, you substitute, R2 is equal to X2. Again, maximum torque formula KE2 square divided by 2x2. This we will get by substituting maximum torque condition in the three-phase induction motor torque formula, that is R2 is equal to SX2. Then I will get KE2 square by 2x2. You see, maximum torque developed by the induction motor is independent of the rotor winding resistance. It is not depending upon the rotor winding resistance. And few more relations, full load torque and maximum torque relation. Full load torque by maximum torque is 2a SF by a square plus SF square. A nothing but slip corresponding to maximum torque. Full load torque by maximum torque is 2 SM SF by SM square plus SF square. We can solve a good number of problems on these two formulas. Very important formulas for solving the problems. And starting torque by maximum torque is equal to 2a divided by 1 plus a square. Again, a is nothing but what? SM, slip corresponding to maximum torque. Next, what is a three-phase input given to the induction motor? This is root 3 VL IL cos pi, where VL and IL are line values of stator supply voltage. And what is the output power? P2 is equal to input power minus stator copper losses. So where P2 is nothing but what? Rotor input. So from stator to power is going to the rotor. This is rotor input. So rotor input P2 is equal to stator input minus stator iron losses and copper losses. Next, mechanical power output at the rotor. Mechanical power is equal to rotor mechanical power is equal to rotor input minus rotor copper losses. And total output power of the induction motor is equal to mechanical output power minus mechanical losses. So let us see the power flow diagram of induction motor or power stages. Initially we give the three-phase AC input to the stator winding, that I am calling as P input. In that power input, some power is wasted in the form of stator iron losses and copper losses, and the remaining power is given as input to the rotor, that we are calling as P2. In that some rotor copper winding losses will be there. Remaining is converted into mechanical power that is developed in the rotor. In that mechanical power, some power is wasted in the form of windage and frictional losses, mechanical losses, and remaining output power is given to the load, that is mechanical output of the three-phase induction motor. So here you see mechanical power output is equal to, already this is completed. And before we go to start the practice beats on three-phase induction motor, and three-phase induction motor is a self-starting induction motor. Very important thing. Three-phase induction motor is a self-starting induction motor. Single-phase induction motor is not self-starting induction motor. So remember. Now first question, an induction motor works with AC power. Next, starting current of three-phase induction motor is going to be large, because in three-phase induction motor there is no back EMF, so it would be 5 to 7 times. Answer is C. The difference in speed between stator field and rotor. Stator field is ns and rotor speed is n. So the difference between ns and n is nothing but what? Slip. Next, when rotor is at standstill, so rotor is at standstill means n value is equal to 0, slip is equal to ns minus n divided by ns, and that is ns minus 0 by ns. So ns by ns equal to what? 1. So slip is 1. The number of slip rings in the three-phase wound rotor in the induction motor is 3. So each slip ring will be corresponding to one phase of the rotor winding. So answer is A. Next question. The speed of the synchronous machine is given by ns is equal to 120 f divided by p. Next, the slip of the induction motor is given by ns minus n divided by ns. ns minus n divided by ns. Answer is A. Next, 8th question. The slip of induction motor normally varies in between. It is around 1 to 5%. Next, a 12 pole P is equal to 12 is given. Three-phase induction motor runs at the speed of 485 rpm. So motor speed N is equal to 485 rpm and supply is 50 Hz. F is equal to 50 Hz. Then what is the slip of the motor? Slip of the motor S is equal to, what is the formula? ns minus n divided by ns. So n is given, we have to find out the ns. So what is the ns value? Ns is equal to 120 f by p. So ns is equal to 120 into f is equal to how much? 50 Hz. f is 50 Hz by p is equal to 12. So 12 10 ja, so it is 500. So synchronous speed is 500. So we got synchronous speed 500. Then slip s is equal to, what is the value? ns minus n divided by ns. So I got the answer. Ns value is 500. So here ns value is ns value I got 500. Then slip s is equal to ns minus n by ns. 500 minus 485 by 500. So that is equal to 15 by 500. So that is equal to 0.03, or we can call as 3%. Answer is A. Next, if the speed of the rotating magnetic field is ns and that of the induction motor speed is n, and which of the following is true? As already we told, speed of the induction motor is always less than the synchronous speed. Rotor cannot catch the synchronous speed. If the rotor is catching the synchronous speed, rotor will not be rotating. There won't be any torque on the rotor of the induction motor. So n value is always less than ns. So answer is C. The frequency fr of the induced EMF in the rotor. So rotor frequency in terms of the stator frequency and slip. So already we told, very important formula, fr is equal to s into f. Next, the synchronous speed of a 10 pole. So p is equal to 10 pole, 50 Hz. F is equal to 50 Hz. The synchronous speed, so we have to calculate ns. So ns we have to calculate. So ns equal to, what is the formula? Very important formula, 120 f by p. So 120 into f is equal to 50 divided by p. That is what? 10. So 10 5 is a, so 50 520 600. So ns is equal to 600 rpm. When the stator supply voltage frequency is f, then the frequency of the rotor current fr is equal to sf. Next let us see. In induction motor, starting torque is dash proportional to the square of the applied voltage. So T proportional to V square, uh, directly proportional. So answer is what? A. So when the supply voltage in the induction motor is reduced by 10%, V is reduced by 10%, then the maximum torque will be reduced by approximately, as we know, T proportional to V square. Then if the voltage reduced by 10%, then the torque will be reduced by 2 into 10%, that is 20%. Answer is C. Next, which one of the following statement is correct regarding induction motor? If the stator voltage is changed, then torque will not change. It's not correct. The motor has no starting torque. No, three-phase induction motor is having starting torque. At high slip, the torque is inversely proportional to the square of the speed. No. At low value of the slip, the torque is going to be proportional to the slip. So answer is D. So this we will get from torque slip characteristics of the induction motor. Next, calculate the slip of 6 pole 50 Hz induction motor. So P is equal to 6, F is equal to 50 Hz. Then what we have to calculate? Slip we have to calculate. S we have to calculate. So what is the S formula? Ns minus N divided by Ns. So what is the Ns formula? Ns is equal to 120 F by P. That is equal to 120 into F is 50 and P is 6 2 ja, so it is 1000. So rotor speed is 950 rpm. So n is 950 rpm. N is 950 rpm and ns is 1000 rpm. Then slip ns is equal to ns minus n divided by ns. Ns is 1000 minus n is 950 divided by 1000. So it is 50 by 1000. So 1 cancel, 2 0. So it becomes 0.05. Slip is equal to 0.05, nothing but 5%. So answer is C. Next, by adding resistance in the rotor circuit of a three-phase slip ring induction motor, the starting current it asking about the starting current is going to reduce and the starting torque is going to increase. Next, consider the following statement with respect to the induction motor. Maximum torque is independent of the rotor resistance. It is correct. Starting torque is maximum when the rotor resistance equal to the rotor reactance. Correct. Torque is very sensitive to any change in the supply voltage because T proportional to V square. It is also correct. So all the three statements are correct. So answer is D. Next, a three-phase induction motor is wound for 4 poles. So P is equal to 4 and supplied from a 50 Hz system. F is equal to 50 Hz, and when speed of the rotor is 600 rpm, n is equal to 600 rpm, and rotor frequency will be, so rotor frequency f dash equal to s into f. See, s is equal to ns minus n by ns. So ns we have to calculate. Ns is equal to 120 f by p. So this is 3 and it is 1500. So 15 slip I'll calculate. 1500 minus 600 by 1500. So 1500 minus 600 is 900 by 1500. So 0 0 0 0 cancel, 3 3 is a 3 5 is a slip is equal to 0.6. So f dash equal to sf, that is equal to 0.6 into f is 50, so that is 30 hertz. So rotor frequency is 30 hertz. Answer is A. Next, if a 6-pole induction motor is running at 50 hertz, so P is equal to 6, F is equal to 50, has an EMF in the rotor frequency of 2.5 hertz. So F dash is equal to 2.5 hertz. Then the speed of the motor will be, so N value we have to calculate. So N is equal to, what is the formula? N is equal to Ns into 1 minus S. So F dash equal to SF. From this we can calculate the slip value. So S is equal to F dash by F. F dash is 25 and F is 50, that is 1 by 2, it is 0.5. So next, Ns value we have to calculate. Ns, so Ns is equal to 120 into F, that is 50 by P, 6 2 ja. So Ns is equal to, we will get 1000. So N value from this formula, N is equal to Ns 1000 into 1 minus 0.5. This becomes 0.5. So half of 1000, that is equal to 500. Sorry, somewhere we have done the mistake. Let us cross check it. If a 6-pole induction motor, P is equal to 6, F is equal to 50 hertz. So sorry, it is not 225, it is 2.5. So it is, F dash is, this is 2.5. It is 0.05. So S is equal to 0.05 and this is 0.05. So this becomes 950 rpm. So answer is 950. So here instead of 2.5 I have taken 25, it is 2.5. Next, a 3-phase induction motor, sometimes copper bars are placed deep inside the rotor. It is done to improve the starting torque of the motor. Answer is B. Next, slip ring induction motor has advantage of, it has high starting torque and high overloading capacity, nearly constant speed, and low starting current in comparison to the squirrel cage motor. Yes, because it has some additional resistance, all of the above. So answer is D. So this is about 3-phase induction motor. We'll quickly see about the transformers. So that topic I will cover here. So this is the, let us say it is the transformer core, and this is primary winding, and it is connected to input supply whose voltage need to be changed, and it is connected to the load. So what transformer will do? Transformer is a static piece of device. It has no rotating parts. It increases the voltage level or decreases the voltage level. So let us say V1 voltage I want to decrease, then I'll be keeping the number of turns less in the secondary. The winding which is connected to the power supply is called primary winding. This I am calling as primary winding. The winding which is connected to the load, is called what? Secondary winding. This winding we are calling as secondary winding. This winding we are calling as primary winding. The winding which has more number of turns is called high voltage winding. The more number of turns. The winding which has less number of turns is called low voltage winding. See how the transformer works. Whenever AC power supply is given to the primary winding, then AC current will start flowing through the winding and it develops the AC flux. when AC flux links with the winding, an EMF E1 will be induced. E1 value depends upon the number of turns in the winding, and the flux developed in the primary winding will travel through the core of the transformer, and again it links with the secondary winding. Then EMF E2 will be induced. Let us say this input voltage I want to reduce, then I'll be keeping the less number of turns in the secondary winding. Input voltage I want to increase, then I'll be keeping the more number of turns in the secondary winding. So as a EMF is there in the secondary winding and it is closed with the load, then current started flowing through the load, that is nothing but what, I2. So this is a basic principle of transformer. Transformer works on the principle of what, mutual induction. So because we are giving the power supply to the primary winding, secondary winding is receiving the power, through the induction principle. So transformer, whenever we give DC power supply to the transformer, DC current will flow, DC flux will be developed. When DC flux links with the winding, there is no EMF. So secondary this EMF, no EMF in the winding means winding gets short circuited. Some voltage is there in the supply and no voltage in the winding, then large current will enter into the winding gets burned. And this is some basic principle of transformer. And there are two types of transformer based on the characteristics of the transformer. So one is ideal transformer and other one is practical transformer. So ideal transformer means it has no losses, no core losses, no copper losses. So it has no losses, and core is made up of purely magnetic material, no leakage of flux in the core. And practical transformer has some losses. And very important equation in the transformer winding, EMF E is equal to 4.44 F pi m n nothing but number of turns. So flux involved in the EMF equation of the transformer is peak value of the flux, maximum value of the flux. It is very important. In transformer, what is the efficiency formula? Output power by input power into 100. So when the transformer will get maximum efficiency, whenever the iron losses equal to copper losses, we will get maximum efficiency in the transformer. And very important bit, why transformer is not rated in kilowatts, or why transformer is rated in always kVA? Because in the transformer we have two losses. One is iron loss depends upon the flux depends on the voltage. And we have copper loss depends upon the current. So total losses in the transformer, they depend upon either voltage or current. They don't depend upon the power factor cos pi. Therefore we don't represent the transformer rating in terms of kilowatts. We always represent in terms of kilovolt ampere. Transformer is rated in terms of kVA. And whenever the transformer is manufactured, what kind of load we are going to connect on the transformer, we don't know. So we can't specify the power factor in the transformer. Therefore transformer is rated in terms of kVA. And on transformer we conduct OC test. OC test is to determine the iron losses, and we conduct the SC test to determine the copper losses in the transformer. In the transformer core, iron losses will occur. In the transformer winding, copper losses will occur. So transformer to reduce iron losses, to reduce eddy current losses, transformer core is laminated. And to reduce the hysteresis losses, transformer core is made up of less hysteresis coefficient material. So this is some very important points related to the transformer. Thank you. I hope all these BW sessions are useful for you. So it was very late sessions. Thank you. All the best for your GENCO exam.